This is Dr. Vermilio. In this lecture, we'll discuss audiogram interpretation from Kramer, Chapter 5. This is Part 3, and this will be on masking and the plateau method. So when is masking necessary? When bone conduction, for bone conduction masking, whenever there is a more than 10 dB difference between the unmasked bone conduction threshold and the air conduction threshold of the test ear or air bone gap. Masking is needed to rule out the possibility that the bone conduction threshold is actually coming from the non-test ear. And for air conduction masking, whenever the difference between the air conduction threshold of the test ear and the bone conduction threshold of the non-test ear is greater than or equal to the interoral attenuation, which is 55 dB for insert phones and 40 dB for supraoral earphones. Masking is needed to rule out the possibility that the air conduction threshold is actually coming from the non-test ear via bone conduction. The masker is always delivered by air conduction with an earphone to the non-test ear. Masking may be delivered with a supraoral earphone or an insert phone or a circumoral earphone. Whenever the non-test ear can hear the sounds through bone conduction, masking is needed. Failure to properly use masking may lead to an improper description of the type of hearing loss, the severity of hearing loss, and or which ear is responding. Why is this a problem? Well, it's a problem because audiologists and surgeons need to make a determination about intervention or management of the hearing loss. And if they do not receive the proper diagnosis, the proper description of the hearing loss and the severity of the hearing loss, they can do things that are inappropriate or wrong for the patient. Figure 518 in the Kramer textbook. Take a look at this. This is in the supplemental topic on masking procedures in Chapter 5. Read about the plateau masking method in the supplement for Chapter 5. So you will have a Moodle quiz assignment on this masking method. And now we'll review the masking plateau method. Masking of pure tone signals heard in the non-test ear is accomplished through the use of narrow band noise, with the center frequency equivalent to the frequency of the test tone. The narrow band noise is delivered to the non-test ear, and the pure tone signal is delivered to the test ear. The narrow band noise is calibrated in effective masking level so that a 40 dB masker would elevate a threshold in the non-test ear to 40 dB HL, providing the unmasked threshold is less than 40 dB HL. The plateau method begins by putting the masker into the non-test ear. At 10 dB SL, raise the threshold, or another way to say it is 10 dB above the air conduction threshold of the non-test ear, commonly referred to as the initial masking level. dB SL means a certain amount above something. So it's 10 dB above something. What's the something? Well, regarding the unmasked air conduction threshold in the non-test ear. Okay, so that's what that means in this case. The plateau method monitors the patient's response to the tone presented to the test ear for different levels of the masker delivered to the non-test ear until the clinician is confident that cross-hearing is no longer a factor. And that's when we reach something called the plateau. All right, so this is a combination of a couple of figures, 517 and 518 in Kramer. This is the part I want you to look at. Let me point out a few things. And some of the information on this you will disregard. We're not going to really discuss it. I want you to focus on this. I want you to focus on the fact that for this ear at 500 hertz, the left ear air conduction threshold is 10 dB. The unmasked left bone conduction threshold is at 5 dB HL. And the unmasked air conduction threshold for the right ear is 60 dB HL. So the question is, when we deliver a sound, a test tone to the right ear at 60 dB HL, is there a remote possibility that actually the left ear is detecting that? Well, how do we decide that? Let's assume supraoral earphones are being used. No, we're going to assume insert phones are being used. Okay, insert phones. So insert phones are being used. What is the interoral attenuation for an insert phone that we're going to use? It is, right, 55 dB. So 60 dB HL presented to the right ear minus the interoral attenuation means that this sound will cross over by bone conduction and reach the cochlea of the left ear at what? 60 minus 55 equals 5 dB HL. Is there a remote possibility that the right ear could hear it? Well, that's actually equal to the bone conduction threshold in the right ear. By definition, the bone conduction threshold means the patient hears a tone at that level presented via bone conduction about 50% of the time. So yes, it is possible for the patient to hear that. Because of that, we now know that there is a need for masking. So we're going to need to put the masking noise in the left ear, which is the non-test ear. And we're going to present the noise at 10 dB SL. 10 dB SL. So that means 10 dB SL ray the unmasked air conduction threshold for the non-test ear. All that means is that, the threshold for the non-test ear, for the left ear, this frequency is 10 dB HL, so we're going to apply 10 dB of masking, and the initial masking level will be presented at 20 dB HL. Look at this graph. The x-axis is masking level presented to the non-test ear in dB HL. This is the level of the tone, the test tone. Sorry, this should be labeled. The level of the test tone presented in dB HL to the test ear. So this is the initial masking level, or the IML, initial masking level. Okay? And that's the start of our protocol. Okay, so to review, 10 dB HL threshold for the non-test ear, which is the left ear. And then 60 dB HL air conduction threshold for the test ear. These are both unmasked thresholds. At the initial masking level is 10 dB above the air conduction threshold in the non-test ear, which is 10. So 10 plus 10 equals 20. 20 dB HL of masking noise represents the initial masking level presented to the left ear. Okay, so the masker and test tone are heard in the non-test ear. And why do we say that? Because without any type of masking noise, the tone is detected at 60 dB. 60 dB. But when we add noise only at 20 dB HL in the non-test ear, and then we play a tone of 60 dB HL to the test ear, the patient doesn't hear it. Okay, and then we raise the level of the tone 5 dB to 65 and ask the patient, do you hear that tone? No. Huh. Okay, remember, we're only delivering 20 dB HL of narrowband noise at 500 Hertz to the left ear or the non-test ear. And that wiped out the ability of the patient to hear the tone at 60. The patient cannot hear the tone at 65. Can the patient hear the tone at 70? Well, that symbol means that's roughly a threshold where the patient can detect the tone. So the lowest level where the patient can detect the tone. Okay, that's great. So when the tone was presented at 60 dB HL with no masking noise, which ear heard the tone? Well, we know now that it must have been the left ear, because as soon as we added just a tiny bit of noise to the left ear, the patient no longer responded to a tone delivered to the right ear at 60 dB. This part of the masking function represents where the masker and the test tone are heard in the test ear. Okay, and this part of the masking function represents the plateau, and this is where the masker is heard in the non-test ear, and the test tone is heard in the test ear. So those are the major things you have to know. But let's take it step by step. Let me go back here. So you know how we found the initial masking level? It's just 10 dB above the unmasked air conduction threshold for the non-test ear, which was 10 dB. So 10 dB plus 10 dB equals 20. That's why we have 20 dB of noise going into the left ear. Can the patient hear the tone delivered to the right ear at 60 dB HL? No. What about 65? No. Can they hear it at 70? Yes. Okay, the next part of the protocol is we're going to raise the level of the masking noise to 25 dB HL according to this protocol. And then we ask the question, when we deliver a test tone to the right ear at 70, can the patient still hear the tone? No. What about when we raise the tone at 70 and the noise is still at 25? Can the patient hear the tone? Yes. Okay, well, we didn't get a plateau. Let's do this. Let's raise the level of the noise again to 30 dB HL. Can the patient hear a tone delivered to the right ear at 75 dB HL? No. What about at 80 dB HL? Can the patient hear the level of, or can the patient hear the tone? Yes, actually, our patient can. So he can hear the tone delivered at 80 dB when the noise is presented at 30. Okay, we still don't have a plateau. Okay, let's keep going. What about at 35 dB HL? If we put that noise in the left ear, will that mask or hide a tone delivered at 80 dB to the right ear? And the answer is no, the patient still hears it. Oh, well, that's a good sign. Now, what if we increase the level of the noise to 40 dB HL? Will the patient still be able to hear a tone delivered at 80 dB to the right ear? The answer is yes. Great. Okay, what about at 45 dB? When we present the level of when we present 45 dB masking noise to the left ear at the non-test ear, can the patient still hear a tone delivered via air conduction at 80 dB HL to the right ear? And the answer is yes. This is called the plateau. And we can actually use a 15, 20, 25, 30 dB plateau. This is actually a 35 dB plateau. So what is the real threshold? The real threshold is actually the level where the patient hears the tone, the lowest level where the patient hears the tone across a range of masking noise levels. This is called the plateau. This is the masked threshold. It means that the right ear was actually hearing the sound. And then we would put this symbol, this triangle, on the audiogram, and that's the masked air conduction symbol for the right ear. And again, the masking noise was delivered to the left ear. Now watch what happens if we increase the noise even more over here. If we increase the noise to 70 dB HL, all of a sudden the patient can no longer hear that test tone delivered to the right ear rather, at 80 dB. We have to raise the level of the tone again to 85. And then when we raise the level of the noise again to 75, the patient can no longer hear the test tone at 85. We have to raise the test tone to 90. So what's happening here? Why do we have this occur? Well, the reason is that the level of the noise is so high that it is crossing over in the opposite direction from the non-test ear. The noise is now being detected by the test ear. All right, so this part of the function, this diagonal right here, and this diagonal right here represents that the noise and the test tone are both detected in the same ear. In this part, in this undermasked part, the noise and the tone are detected in the non-test ear, or the left ear. On this part of the function, the noise and the tone are detected in the test ear. Now, of course, the noise is still being delivered to the non-test ear, but the point is that the test signal and the noise are heard in one ear, which would be the test ear. All right? So, again, the masker and the test tone are heard in the non-test ear. the masker and the tone are heard in the test ear. And the plateau means that the masker is heard in the non-test ear, and the test tone is actually heard in the test ear. That's great. And the other thing to be aware of is that the test tone is always delivered to the right ear, though it may be detected in the left ear, depending on the hearing configuration and the masking that's used. And the masking noise is always delivered to the left ear, but it could be heard in the test ear due to a high presentation level and crossover. Okay, so our masked air conduction threshold is really 80 dBHL. Okay, so note, any sounds below the level of the masked threshold will be inaudible to the patient at that masking level. For example, when the narrowband noise is presented at 40 dBHL, right here, 40 dBHL, to the non-test ear, a tone of 70 dBHL presented to the test ear will be inaudible. So anything below the level of these, when we should put the word threshold in quotes, right? These actually aren't really thresholds. We didn't use the Hewson-Westlake protocol. All we did was add noise and then ask the patient, can you hear it? No, you can't hear it. Okay, we raised the level up 5 dB. You hear it? Okay, great. Then raise the level of the noise up, etc. So these aren't really true thresholds, but we're going to handle this data as though these are thresholds. And just so you know, this graph right here with the masking plateau is not actually used in the clinic. Audiologists do all of this in their head. So we just do this in our heads as we're doing this masking protocol. Can we forget it where we are if we get distracted? Yes, that happens all the time, and then we have to start the masking plateau over again. So that's the masking plateau method. So now you are ready to answer the questions for the masking homework in Moodle. And this will take you through all the aspects of this figure. Okay, audiograms are used to describe the degree or amount of hearing loss, the type of hearing loss, and something called the shape of the hearing loss. We have degrees of hearing loss. This is found in the Kramer textbook. It's also from the ASHA guidelines. Air conduction thresholds are used to define the degree of hearing loss. Recall that the average threshold for normal hearing is 0 dBHL. By convention, we generally call the range of normal from -10 to 25 dBHL. Also recall that 0 dBHL does not mean the absence of sound. Now, normal, this is kind of misleading. It says degree of hearing loss, but a normal degree of hearing loss, that doesn't make any sense at all. A normal degree of hearing loss for adults, that doesn't make any sense. But anyway, here it is. So a normal threshold is from -10 to 15 for children. And for adults, it's actually -10 to 25. That actually should say -10, though I think in your text it says 16. So this is not considered a hearing loss. So we would not consider this representative of a hearing loss, but normal pure tone thresholds, okay? Now, anything poorer than or higher than 25 dBHL is considered a mild loss if it's between 26 to 40 dBHL, a moderate loss if it's 41 to 55. And again, we could look at this frequency by frequency on the audiogram. A moderate severe loss to 70 dB. A severe loss would be up to 90, and something called a profound hearing loss would be something greater than 90 dBHL. So this determines the degree of hearing loss. You know how to determine the type of hearing loss. That's looking at the air conduction thresholds and bone conduction thresholds. Then you could determine the degree of hearing loss by looking at the air conduction thresholds. That's what's used to determine the degree of loss. And for degree of loss, we either have normal pure tone thresholds or we have a mild through profound type of pure tone threshold loss. Caution, the values listed are those from the text and from ASHA. They are not necessarily the values that are used by every audiologist. For example, the VA Medical Center in 1982 These are the range or the categories for the pure tone degree of, excuse me, these are the ranges for the degree of loss. Okay? And in the Kramer text, these are the ranges for the degree of loss. And notice that while they're similar, they can be a little bit different. 0 to 20 represented normal. For adults at the VA hospital doesn't actually test children. And then a moderate loss was considered from 45 to 65 in the VA. According to ASH, it's 41 to 55. There was no category for a moderately severe loss at the VA at that time. And then 70 to 110 dB HL represents a severe loss for the VA back in 82, but 71 to 90 represents a severe loss. And a profound loss at the VA back then was when you had no response. And for ASHA, it's 91 plus, or anything greater than 90 dB HL. That represents a profound loss. So imagine yourself on the phone, you're talking to another audiologist, you're talking to an audiologist or a speech pathologist, and you say, what type of hearing loss did they have? And you say, oh, they had a severe high-frequency hearing loss. Well, if they went through the VA system and didn't look at the current ASHA guidelines, they might be thinking in terms of this range, whereas if they were a newer graduate or they've reviewed the ASHA guidelines, they would be thinking about this range. So that's just food for thought. It is also important to be cautious in assuming that these categories accurately apply to a patient's perceived communication difficulty. They are merely a conventional and convenient way to describe the audiogram. So a severe hearing loss might not necessarily mean a severe communication impairment. And on the other hand, normal pure tone thresholds might not mean the absence of any type of hearing disability. Okay, the types of hearing loss, again, are determined by the bone conduction thresholds and the air conduction thresholds. Sensory neural hearing loss means that we have an air-bone gap less than or equal to 10 dB, and the air conduction thresholds are poorer than 25 dB HL. Conductive hearing loss means that we have an air-bone gap greater than 10 dB, or you could say 15 dB or higher, and the bone conduction thresholds are less than or equal to 25 dB, and the air conduction threshold is greater than 25 dB HL. A mixed hearing loss, air-bone gap is greater than 10 dB, and the bone conduction threshold is greater than 25 dB. That would represent a mixed loss. The site of lesion for sensory neural hearing loss, again, is the sensory organ for hearing, which is the cochlea. So the site of lesion or the problem is in the inner ear or in the neural pathways from the 8th nerve through the brainstem auditory pathways and up to the cortex. The site of lesion or the problem can be in any of those areas or all those areas. A conductive hearing loss indicates that the problem is in the external ear canal or the middle ear, and a mixed hearing loss indicates that the problem is either sensory neural or in the ear canal, and in the ear canal and or the middle ear. Other descriptions of hearing loss include bilateral, which refers to both ears. Unilateral is sometimes used in reference to a hearing loss if it is only in one ear. Asymmetric is sometimes used when there is a significant difference in the hearing loss between the two ears. Asymmetric. And here are a few audiometric configurations from Kramer, figure 6.9. You see a relatively flat hearing loss, a sloping hearing loss, a rising hearing loss. This is the famous corner audiogram, meaning that the pure tone thresholds are only at very high levels and only in the low frequencies. This is a precipitous loss, sort of like a cliff here, right? So this is a precipitous high-frequency hearing loss, and this is a notched hearing loss, and you know what this notch would be from typically. Noise exposure, and this is due to exposure to high levels of sound, coupled with the presence of the ear canal resonance. Okay, imagine presenting test tones at 1,000 hertz to the left ear, and we keep increasing the level, and we find that when the level is presented at 100 dB HL, the patient still doesn't respond, still doesn't push the button. In that case, we will put a little arrow on that symbol. That means that this is a no response. This is not a threshold. This means that we presented, or the audiologist presented, the sound at the limits of the audiometer, which in this case are 120 dB for a 1,000 hertz tone, and the patient still did not respond. So it's saying, you know, we tried, but we didn't get there. Same with these bone conduction thresholds. This is actually the limits. Remember we talked about the limitations of the output of the bone conduction transducers? This is the limits of the output. So does this represent an air bone gap? Is there an air bone gap for the left ear? And these are all masked bone and air conduction symbols. And the answer is no. All we know is that there were no patient responses at the output limits of the audiometer for bone and air conduction testing. We don't know if what are the real bone conduction thresholds. We don't know what the real air conduction thresholds. When it comes to describing the type of loss, we could say, oh yeah, this is definitely a profound loss, because if the bone conduction thresholds are present, they're at a level higher than this. But we cannot say that the patient has a conductive loss. We'd actually have to do something else to infer the presence of a conductive loss. We'd have to do a different type of test. Tactile responses. Tactile or vibral tactile responses are a result of the patient feeling the vibrations rather than hearing them. This mostly occurs by bone conduction for 250 and 500 hertz. The patient should be asked if he or she felt the test signal in these cases, and it should be noted on the audiogram. So here is an audiogram with some tactile responses for the bone conduction symbols. So bone conduction thresholds. So the patient doesn't respond, and then finally 50% of the time, this is the lowest level, where the patient responds when the sound is delivered via bone conduction to the right ear, and then we need to ask the patient, excuse me, did you actually hear that, or did you mostly feel it? And if they say that they feel it, then we could write VT next to that symbol, and VT means vibrotactile. The patient actually doesn't hear it, the patient feels it. Okay? We talked about supraoral earphones and a collapsed ear canal, and elevated pure tone thresholds from a collapsed canal, and a high-frequency air bone gap, a high-frequency conductive loss. This is a high-frequency conductive loss, but it's secondary to the presence of a collapsed canal because we were using supraoral earphones. These symbols, in this case, the air conduction symbols, are not real. Air conduction thresholds are probably closer to this. So if we tested the patient again, see it says supraoral earphones here. If we tested the patient again with insert phones, most likely these air conduction thresholds would go up. Okay. You would also see this if the patient had occluded ear canals with cerumen. So if the patient is a Q-tip user, you could also see the same type of loss with a Q-tip user. Or if the patient had an earplug and you didn't bother to check the ear canals before you tested the patient, just put the headphones on the patient with nice foam earplugs on, you could also see this type of conductive high-frequency hearing loss. It is not real. Okay. And this says everything I just said. So a supraoral earphone may result in an artificial air bone gap for the high-frequency thresholds. In this case, the elevated or poor air conduction thresholds are not real. Insert earphones will not cause the collapse of an ear canal. This is another advantage for using insert phones. When you see air bone gaps for the high frequencies only, suspect a collapsed ear canal or an occluded ear canal with the earwax. You'd have to look in the ear with the otoscope to verify that. Most likely in this example, the real air conduction thresholds for 2,000 and 4,000 hertz are closer to the bone levels for the bone conduction thresholds. Pure tone average is a summary of pure tone thresholds over a particular range that is important for speech understanding. The traditional pure tone average is the average of the thresholds for 500, 1000 and 2000 hertz. Other pure tone averages include a 4-frequency pure tone average, for example, for 500, 1000, 2000, and 3000 hertz, or a high-frequency pure tone average for 1000, 2000, 3000, and 4000 hertz. Do not use pure tone averages as a guide for describing the degree of hearing loss, though in the early stages, in some very early papers, that's exactly what they did. They used the pure tone average to describe the degree of hearing loss. That's not what's commonly used in the clinic. Decibels of sensation level, we discussed this before. dBSL, the reference value is the pure tone threshold or the traditional pure tone average. And actually it could be the SRT also. The 0 dBSL indicates the level at threshold, or that the level is equivalent to the level at threshold. 10 dBSL indicates a level that is 10 dB above the threshold. The threshold in dBHL plus the value in dBSL equals the presentation level. Okay? So if you were at a clinic and you saw on the audiogram that the word recognition score was presented at 15 dBSL, rated the SRT, and actually we haven't reviewed these speech tests yet, but just to give you a heads up, all that means is that 15 dB HL was added to some threshold. In this case, it was the speech, something called the speech reception threshold that we'll talk more about. When we talked about masking, the masking noise for the non-test ear was initially presented at 10 dB SL, rated the unmasked threshold for the non-test ear. So you look at the unmasked threshold for the non-test ear, which in that case was 10 dB HL, and then you just add the level in dB SL, which is 10. So the initial masking level was 20 dB HL. Okay, and that's the end of our lecture for Chapter 5.